Okay, last time we finished up chapter 2, and again, the little part of 3, which was electronegativity tied to the periodic trends, which again is the only thing you really need to know for exam 1 from chapter 3, again, is the electronegativity, what it is, how it ties to periodic trends like we talked about. Our exam should be coming up. I misscheduled the day, so I think it's coming up a week from Tuesday instead of maybe next week, but we'll go for a week from Tuesday. And again, it will cover chapter 1, chapter 2, and again, just electronegativity in terms of the trend of what it is and the periodic trend. So this now will be really into chapter exam 2, I guess, exam 2 material here. So in this chapter, we're going to talk about bonding, and we're going to talk about both types of bonding, really, even though it says covalent bonding. We're going to talk about ionic and covalent bonding in this chapter. And we'll go through this chapter. We will then hit the next chapter, which really does sort of tie together with this chapter. The next chapter is everybody's favorite thing, which is geometry and polarity and some other new stuff in terms of bonding that you might have not seen before. And then we'll actually come back, I think, to this chapter at the end of that. And I think there's some nomenclature stuff at the end of this chapter that we'll come back to and kind of do all the nomenclature stuff together. But we're going to first start with bonding here. And as I mentioned, we're going to talk about both types of bonding. And one way that we represent bonding, both ionic bonding and also covalent bonding, is that we use Lewis dot symbols. They are sometimes just generically called electron dot symbols as well. Same thing, basically. Lewis is a guy that's very big in bonding, but electron dot symbols or Lewis dot symbols are really the elemental symbol and one valence electron for one dot for each valence electron that it possesses. As we talked about last time with sort of the atom, when we do form a chemical bond, it is the electrons that basically come in contact with each other. If you think about, again, the structure of the atom, we have electrons flying around on the outside. So obviously when they come close to each other, the electrons are going to say hello to each other, and they are the ones that are involved in bonding. Now, there are two types of electrons that we talked about. When we talked about electron configuration, again, there are core electrons, which are closer to the nucleus, also held a lot tighter because of that, and they are not involved in bonding. It is the valence electrons that are involved in bonding, and these are the highest energy electrons. They are really the furthest from the nucleus. And remember, as we talked about last time as well, you can write the electron configuration if you like to figure out the valence electrons, but really a much quicker way is they are equal to the group number on the periodic table. So the number of valence electrons will equal the group number. Definitely for our representative elements, which again is our normal A counting of the groups, our 1, 2, skip the middle, 3, 4, 5, 6, 7, and 8. The good news is in bonding, we really don't deal too much with any transition metals, so you don't have to worry too much about valence electrons there, even though they are also equal to the group number. And as we talked about, again, those transition metals have the S's and also the D electrons that they could use really as valence electrons. But for the most part, most of the bonding that we talk about here, and in most cases, really will only deal with really the representative elements and not really the transition metals. So again, the valence electrons will equal the group number. As I mentioned before, we basically use the elemental symbol, and we use one dot to represent each of the valence electrons. There really is kind of no necessary rule in terms of how you do that, but most people will a lot of times do one at a time clockwise and then kind of go back and pair everybody up. It really doesn't matter. The only thing that you can't do is you can't go more than 2 per side. So basically 2 per side is basically what you got to do. And since there are 4 sides, that means the maximum number of electrons in most cases is going to be lucky number 8. Yeah. And again, 8 on the periodic tables are noble gases. So as we'll talk a lot about as we go through this chapter, once again, that is pretty much the basis of all bonding, why it sort of occurs. Both ionic bonding and covalent bonding is for everybody, again, to become, as we talked about last time, isoelectronic with the noble gases, basically to achieve the same electron configuration as the noble gases because they're really stable, and that's basically what we want to do. So here's something I made when I was bored. I know, should get a hobby, but here we go. Some Lewis dot symbols here. We got 1 in everybody, 2, 3, 4, 5, 6, 7, 8. Remember that our friend helium, which is part of group 8, only has 2 valence electrons, and that's because helium only has 2 total electrons. So they're both valence electrons, but everybody else in group 8 will have 8. That is also why another really, I'll say it one more time, really important aspect of bonding is our friend hydrogen. In order for hydrogen to get to noble gas configuration, he only needs to get to helium, which is the noble gas that comes after him. That is why our friend hydrogen only does 2 when he's doing bonding. So something to keep in mind, hydrogen only 2 electrons only. So basically, hydrogen should always look like this, basically just one line that represents 2 electrons. If you ever at some point find yourself drawing dots all around hydrogen, you could also draw a big X around it as well, because it is definitely wrong. Or my favorite people just like to also triple bond it for good measure. So it's got 40 million electrons, right? So again, only 2. Hydrogen only needs to get to basically helium. Everybody else on the periodic table has got to get to group 8, where they have 8 valence electrons. And that's why 8 and 2 are really important numbers in terms of bonding. And obviously, they're an octet rule and duet rule, which we'll talk a little bit more about later on. So let's talk first off about the 2 different types of bonding and really what the difference is between those 2. First off, we could have an ionic compound, and in an ionic compound, it will always be pretty much a metal and a nonmetal coming together. And as we talked about with our periodic trends, metals and nonmetals have pretty opposite periodic trends. We know that metals typically want to hang on to their electrons or lose their electrons. Metals typically want to lose their electrons, right? They have all those periodic trends like low ionization energy, low electronegativity, low electron affinity. They're not really interested in hanging on to their electrons. Nonmetals, on the other hand, have all the trends that are opposite of that. They want to hang on to their electrons, and they also want to bring electrons towards themselves. So they're more apt to gain electrons. So whenever you get a metal and a nonmetal together, that is what you're going to have happen. You're going to get, again, a transfer of electrons because of the differences in those periodic trends. The result of that, as we may know, is the metal will form a positively charged ion, which is a cation. The nonmetal will form a negatively charged ion, which is an anion. And it is that electrostatic attraction that holds that together. Also, a very important thing to know, there is absolutely positively no sharing of electrons here. Yeah. So an ionic compound is simply held together by the attractive forces between the opposite charges. In this case, there is such a difference in the periodic trends and all those sort of properties that we actually get a full, like, electrons jumping ship from the metal to the nonmetal because they're going to get rid of them, and the nonmetals are going to be very happy to pick those up. Now, the other type of bonding are covalent compounds, also sometimes referred to as molecular compounds as well. Here, this is typically between 2 nonmetals. And again, if we think about the location of nonmetals on the periodic table, they're all pretty much sitting in the exact same location-ish. And what that means is they have pretty much very similar periodic trends in terms of things like ionization energy, electron affinity, electronegativity. So what happens in the case where, again, we get two nonmetals that come together, they both are like, I don't want to give up my electron. And they both are like, I would rather take your electron. And this is the actual conversation that's probably happening. And the best that they do in that case is, because they both really want to hang on to their electrons, they both really want to kind of take electrons. The best that they could do is actually share the electrons. So they sort of agree upon, well, I'm not going to give up my electron. You're not going to give up your electron. How about we just share them? All right. And we get some type of sharing of electrons that basically occur. As we will talk about in this chapter, that sharing may be equal sharing, or that sharing may be unequal sharing. But in a covalent bond and in a covalent compound that has covalent bonds, there is some aspect of sharing that's basically happening here between those elements. And again, the reason for that is they have very similar trends in terms of those properties. So the general rule tells us that things with low ionization energy will tend to form cations. And again, things with low ionization energy, which is the energy required to remove an electron from an atom. So if you have very low ionization energy, it doesn't take a lot of convincing for that electron to be removed. Well, typically we lose those electrons, become positively charged, because they now will have more protons than electrons. And things with high negative electron affinity, remember, electron affinity is the energy change that occurs when somebody gains an electron. And that increases as you go to the upper right of the periodic table and decreases as you go down. Those guys will tend to form anions. So if you have a pretty high electron affinity, that means you probably picked up some electrons along the way, and you're going to become negatively charged. Any questions on that there? All right, so general rule tells us, again, kind of our metals will form cations, our halogens, oxygens in that nonmetal region, a lot of times will form anions, especially when we do get a metal and a nonmetal together. So let's take a look at this. And here we have lithium fluoride, and we're going to put together basically lithium and fluorine. And the first thing that you might want to sort of figure out is what you're dealing with. So hopefully, you know, lithium is a metal, and fluorine, which is fluoride, is a nonmetal. By the way, as soon as you see that combination, you should automatically know that this is an ionic bond, yeah, an ionic compound. Always metal, nonmetal. You pretty much do not need any other hint to figure out what type of bond you got going on there. If it's metal, nonmetal, it's ionic. Again, because of those differences, we are going to see those electrons transferred. So we can represent this ionic bond through Lewis dot symbols. So if we take lithium, which is group number 1, it will have one valence electron. And as was up there a second ago, is electron configuration 1s2, 2s1. This guy right here is the one valence electron, right, that we are talking about right there. We have fluorine, which is group number 7, which means it will have 7 valence electrons. Also an electron configuration of 1s2, 2s2, 2p5. It is these guys right here that are the 7 valence electrons that we see in fluorine. So what happens in this case, by the way, they don't have charges at this point, but what happens is when our lithium and our fluorine get near each other, that's the point where lithium's going to go, take my electron, please. And fluorine is going to be more than happy to grab that electron there. The electron's going to shoot on over, and we're going to get that transfer that's going to occur. The result of that transfer of electrons will result in our lithium losing an electron, which means it now will become positively charged as the electron basically just jumped ship. Our fluorine will pick up that one electron, and it now will become negatively charged because it now has more electrons than protons in this case. And that is how we will represent the ionic bond formation. there are a couple of things that are important here. When I drew this, because this is an ionic bond and because there is absolutely no sharing of electrons, these are ions, which means you do need the charges when you draw these things. And typically speaking, people will put one, if not both of these ions in little brackets there to kind of separate them out. That indicates that there is no sharing of electrons that are happening in this case. First off, any questions on that there? So what happens in terms of electrons for each of these guys? Well, lithium with a +1 charge pretty much gave up this electron right there, which means lithium with a +1 charge will have an electron configuration of 1s2. That is how many electrons? That is 2. Who on the periodic table is 2? That's our friend helium. Yeah. The fluorine had room in its p subshell, right about there, because it could hold 6, to pick up that electron that came over, and that's where it placed it. So fluorine that now becomes fluoride, the ion, will now have an electron configuration of 1s2, 2s2, 2p6. That is a grand total of 10 electrons. Who on the periodic table is 10? That is neon. Again, this is the purpose of bonding. Both lithium and fluorine in this case, they were both able to achieve noble gas configuration by transferring of the electrons from the metal to the non-metal. They both achieve that noble gas configuration. Much like we talked about when we were talking about sort of electron configuration for our uh, representative elements, the metal, when it loses electrons, will back up to the noble gas that comes right before it. So there, lithium backs up to helium. And if you look at fluorine, it actually goes forward on the periodic table as it gains electrons to the noble gas that comes after it. So they both are isoelectronic with the noble gases. They have now achieved that nice, stable electron configuration like the noble gases, and they're going to live happily ever after until somebody comes and splits them apart, like water or something like that, but they will stay in that form. Any questions on that there? So again, the importance of drawing this is to make sure you show the charges because, again, they are ions and, again, some brackets. Now, if we take a look at that unit, that, again, is an ionic bond. The positive negative attraction is what's holding that together. And, again, no sharing of electrons. And as we also talked about last time, the greater the sort of charge is, the bigger the numbers. Again, the stronger that attractive force is. That attractive force is one of the strongest attractive forces you could have. It's usually considered what is referred to as an intramolecular force, which is ionic bonding. And it is so strong that, frankly, if you tried to heat an ionic compound, as I might have mentioned before, it will just start to melt before it will actually break apart and go into the gas phase. So it will, that's a super, super strong force that holds it together. Now, if we take a look at another example here, which is calcium oxide, again, we have calcium, which is a metal. We have oxygen, which is oxide, which is a non-metal. So once again, that is all we need to know, that this is going to be an ionic bond. If we look at the calcium, which is group number 2 on the periodic table, it should have a couple of valence electrons. It also will have an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 are argon 4s2, if you prefer to do it that way. These right here would obviously be our 2 valence electrons that we are talking about. Oxygen is group number 6, which means it will have 6 valence electrons. It also will have an electron configuration of 1s2, 2s2, 2p4 in this case. And Once again, in this situation, what's going to happen is we're going to get that transfer of electrons. In this case, calcium will send over an electron here to our oxygen. And by the way, if calcium were to just lay it up right there and just give away one electron, would it be happy? It would not be happy, because if you look at the periodic table, if it just loses one electron, it now becomes like potassium, which is not a noble gas, right? So it definitely wants to lose both of those electrons. So it will send the other one over as well in this case. That's going to allow our calcium now to have a +2 charge because it got rid of 2 electrons. Our oxygen will pick up those 2 electrons and fill out basically 8 here and end up with a -2 charge in this case. Now, in terms of the electron configuration, what happens when our calcium loses these 2 electrons? It essentially becomes argon's configuration, right? And that is a noble gas. It has 18 electrons. Our oxygen has room for those 2 electrons that can enter right there, because again, that p subshell could hold 2 or 6 total. And that will give us 1s2, 2s2, 2p6, which once again is neon's configuration. So again, here we see that both calcium and oxygen, by transferring electrons, sort of giving away electrons and also accepting electrons, are able to reach noble gas configuration again that makes them really stable. I think we talked about it last time, but once again, is calcium with a +2 charge actually becoming the element argon in this case? It is not. So remember that the only way that you could change an element, right, is to change the number of protons, right? So that's the most important thing. So again, it is still calcium because it still has 20 protons, but it just has the same electron configuration as that noble gas. Same thing with the oxygen. The oxygen is still oxygen because it still has 8 protons. But again, it now will have 10 electrons, which makes it more stable and like noble gases. So again, sometimes people have a misunderstanding about, like, they think the elements change at the noble gases. Again, they just have the same electron configuration as noble gases. Any questions on that there? So when we look at, say, what happens if we put together 2 of those things that we just talked about, which is our friend calcium, and we put it together with fluorine, for example? So again, calcium having argon 4s2, again, those being the 4s2 electrons, which are our valence electrons. Our fluorine 1s2, 2s2, 2p5. Once again, those being our 7 valence electrons that we see in this particular case. Calcium is still a metal. Fluorine is still a non-metal, which means we are going to get the transfer of electrons that we would expect. And when calcium sends it over here to the fluorine, it again is going to lose 1 electron. And again, that is not going to be so great for calcium, as we just talked about, because it's only going to get it to potassium. Can that fluorine at this point take any more electrons? That fluorine is now filled because that 1 electron is going to end up here. So that creates quite a problem for calcium because it wants to get rid of both electrons. Otherwise, it's not going to be happy, right, to reach noble gas configuration. That fluorine there is going to be happy because it picked up 1. But to fix it, we actually will need not 1 fluorine, but we actually need 2 fluorines. Now, this second fluorine also has an electron configuration 1s2, 2s2, 2p5. And it also has space now for this calcium to lay up its second electron here. And this is going to give us, on the other side, calcium that now has made a +2 charge. laying off an electron to each of the fluorines. Each of the individual fluorines will gain only one electron, which means it actually has a -1 charge, each of them. And when we look at what happens with sort of the electron configuration of all three of these ions now in this case, our calcium was able to give up both of those valence electrons, which means once again, our calcium with a +2 charge has reached argon's configuration. Each of the fluorines were able to pick up one electron, which means that each of these fluorines has an electron configuration of 1s2, 2s2, 2p6, or that is again neon's configuration. So in this case, all three of these ions, through gaining and losing electrons, are able to achieve noble gas configuration, and that's why you need to draw two of those fluorines in that case. Any questions on that? That is also why, if you remember maybe from your previous class, when you talked about ionic compounds and you talked about writing the formula for things that have charges, like a positive calcium and a negatively 1 charged fluorine, when you put those together, the overall charge needs to equal 0, which is why we actually need one more of those, right? -2 overall, +2 gives us 0, which is why the correct formula for calcium fluoride is CaF2. The real reason why we put them together to equal 0 in the simplest way possible when we do ionic compounds formulas is this is the reason. It allows everybody to achieve noble gas configuration. Now, if you laid up like, CaF, right? This will now have again an overall +1 charge. That means that calcium was not able to reach its noble gas configuration, and this is not going to be a very stable situation, which is why it doesn't happen. That is why we do need, again, both of those guys to accommodate it. So the real reason, again, why when we write formulas for ionic compounds, metals and nonmetals, cations and anions coming together, all the positive and negative charges need to equal 0 in the simplest way possible. And the real reason, again, is this reason. It's the bonding aspect of it that allows everybody to be really stable and reach that noble gas configuration. Any questions on ionic bonding there? Okay. Then let's talk about the other type of bonding, which is covalent bonding. Feel like my dots and lines definitely missed. Covalent bonding, as I mentioned before, is between two nonmetals. And once again, as I mentioned, because of those periodic trends, this is going to be some sharing of electrons going to happen in this situation. And that again is because neither one of them want to give up their electrons, so they will share. Gilbert Lewis suggested the role of electron bond formation, hence Lewis structures, which is why they're called that. And he thought of it as, I'll just redraw this since my lines went all astray. I think they're okay on your handout if you're looking at it. Hydrogen here, for example, has one valence electron. And if we had another hydrogen atom there, it would also have one valence electron. Clearly, in this example, they are both hydrogen, which means they have the identical trends. They have identical electronegativity, identical ionization energy. Neither one of them is going to want to give up its electron. So in this situation, we're going to get some sharing of those electrons that's going to happen. And we're going to get a covalent bond formation, which you can represent with two dots. And these dots basically represent the sharing of electrons. In this particular case, those two dots that are shared between that atom counts for the hydrogen on the right, and it also counts for the hydrogen there on the left. So those two electrons would be shared. That would give the hydrogen on the left technically 2 electrons, and that would give the hydrogen on the right also 2 electrons. And as I mentioned before, hydrogen just needs to go over to helium, right? And helium is number 2 on the periodic table, and that is a noble gas as well. So that's going to make it a very happy bond right there. By the way, 2 dots, which is one single bond, can also be represented by a line. So sometimes those electrons being shared is represented by a line. One line represents two dots, which is a single bond. A double bond, as we'll talk about, is two lines representing four total electrons, or two pairs. And a triple bond is three lines representing six total electrons, or three pairs of electrons as well. You could use, again, lines or dots when you're drawing these things. I personally will use most of the time lines to represent electrons that are being shared. They're referred to as bonding electrons. But again, it's not wrong to use dots if you want to use dots to do that. This is a covalent bond, and it is actually the sharing of electrons that holds that together. Remember that we have, if you want to think about it here, a big positive nucleus, right, happening there. And we have these electrons, which are negatively charged there. So there's going to be some attractive force to that guy's nucleus. There will also be sort of an attractive force to that guy's nucleus. So that dual sort of attraction between the two atoms is what sort of locks those electrons into place between them and holds everybody basically together, so things just don't jump off and leave. Any questions on that there? So as I mentioned, that dual attraction to the nuclei is what holds that together. As we will talk about in this chapter, again, the bonding there, or the sharing, can be equal. So in the case of hydrogen, for example, it is going to be nice equal sharing of those electrons. But there are cases where the sharing of electrons will not be equal. And that will create, as we will talk about, different types of covalent bonds. So covalent bond in general is just the idea that we're going to share electrons to hold those atoms together. But there is actually more specific sort of classifications of covalent bonds that we'll talk about. And that is based on how the electrons are actually going to be shared. Same thing here. If we put two fluorines together, they each have 7 valence electrons. Once again, here, our fluorine is going to have the exact same periodic trends. Neither one's going to want to give up its electron. So it will result in a bond forming between the two, where those electrons, once again, are going to be shared. And again, like you can see on the bottom there, you could draw it with all dots, are for those electrons that are being shared. Instead of the dots, you could draw a line, and you draw the dots around the rest. Once again, in this particular case, those two electrons in the middle count for the fluorine on the left, which gives it 8 electrons. Those two in the middle also counts for the guy on the right there, which gives it 8 electrons. Once again, that will move both of the fluorines into noble gas configuration in terms of their electron configuration. Again, going to make it really, really stable as well. Any questions on that? When we look at this Lewis structure, there are different types of electrons. So all the electrons that are not involved in any type of bond formation, they're just represented by dots, which would be all these guys. These are what are sometimes referred to, if you're old like me, and I will probably call it that a lot, is what are referred to as lone pairs. They are more commonly nowadays in textbooks referred to as non-bonding electrons. So non-bonding electrons and lone pairs are pretty much the same thing. They are the ones that are not involved in any type of bond formation. I know they're not involved in bond formation because, frankly, there's no element written on the other side of them, right? So there's nothing there. Now, the ones where we can use a line to represent the electrons, or you could also use dots, which is involved in really the bond formation here, also has a very special name, which are known as bonding electrons. Very creative. So bonding electrons are the electrons involved in a bond. Non-bonding electrons, or lone pairs, are not involved in bond formation. Regardless if it's non-bonding electrons or bonding electrons, you should always include all of them on your picture when you draw these things. So when you draw Lewis structures, you should always include both the non-bonding electrons and the bonding electrons. And later on, we'll talk about the steps to draw proper Lewis structures for covalent compounds here. All right. So a Lewis structure is, again, a representation of covalent bonding, where, again, we can use the line to represent a pair of electrons that are bonding electrons that are being shared, or you could use two dots. Remember that when we do look at a Lewis structure, it is just the valence electrons that are present. It is not all the electrons, so each of these elements have more electrons, but only the valence electrons, the higher energy electrons, which are involved in bonding, are what we see in our Lewis structures. So again, if we were to draw the Lewis structure here for our friend water, we will see in this particular case here, again, if you did it like we have on the left there, we would end up with something like this. And in this situation, with the oxygen sharing a pair of electrons with the hydrogen on the left and the hydrogen on the right, that is going to be enough for the hydrogen to achieve that noble gas configuration and move it over to neon's configuration. Our oxygen, by sharing those electrons as well for itself, will actually pick up some electrons and move itself to 8, which will also make it very happy and, again, hit that noble gas configuration. Here in this case, both hydrogen and oxygen, remember, even though hydrogen is way over there on the left, hydrogen is still really a nonmetal, right, in most cases. So it is going to really be sharing electrons, even though in certain applications you would think of hydrogen as like losing electrons, but and have a +1 charge. But in this application, again, they're going to have sort of sharing of electrons that's happening. So clearly, we've been talking about 8 and 2. So officially, the 8 and 2 are the important rules for bonding. And that is the octet rule, which basically states that everybody will continue to make bonds until they have 8 valence electrons around them. And again, that allows them to achieve noble gas configuration, except for obviously our most important guy there, which is hydrogen, which should only have 2. And again, that allows it to get to helium. And that is sometimes referred to as the duet rule. And again, as I drew before, don't decorate hydrogen with dots all over. For some reason, people like to go crazy with hydrogen. Carbon's a close second, especially if you go to organic chemistry. Carbon's a close second. People start drawing organic molecules with carbon. Before you know it, it's got like 40 bonds and it just keeps on going and stuff like that. So, but hydrogen is very common in general chemistry to kind of be drawn incorrectly. We talked about some of these multiple bonds, but here are some examples of it. Again, a single bond is the sharing of 2 electrons, which is a pair of electrons, and once again can be represented as either a single line or a pair of electrons there. In certain situations, that is all you need for somebody to basically reach the octet rule and be happy. All you need is single bonds, yeah? Also a very common thing I'll say a lot in this chapter, which is people like to like double bond and triple bond right out of the box when they start drawing things, and that's usually not a great idea. So you usually want to save, as we will talk about, double bonds and triple bonds for situations where you need to fix something rather than double bond, triple bond right out of the box. So, if everybody could be satisfied with a single bond, a lot of times that is the best situation and you don't need to add more things. But there are situations where you do need to get to the octet rule. Sometimes you will need a double bond to achieve that. And something like carbon dioxide is an example of that. Here, the carbon is sharing a double bond actually on both sides there with the oxygen. The result of that is this carbon will now have 8 electrons, and each of the oxygens will also be able to achieve 8 electrons by sharing in a double bond fashion in this case. So a double bond, again, can be represented in bonding electrons as 2 lines, are again sharing 2 pairs of electrons, which is a grand total of 4 electrons. Now, in certain cases as well, double bond is not going to cut it. It's not going to allow everybody to be really happy and hit that sort of noble gas configuration. It's at that point where if the double bonds really don't cover it, then you might need to go to a triple bond to sort of cover that situation. And certain things do need a triple bond to fix it, as is the case here with our nitrogen. Here, by sharing in the triple bond, we get 8 electrons for each of those nitrogens that are present. And again, a triple bond is represented by 3 lines, or not like that, but 3 lines and 3 pairs of electrons as well. Once again, in this case, our hydrogen only still needing 2 electrons in this case, right? Again, just by sharing with that carbon in this particular case. So carbon is a very common thing, making single bonds, double bonds, and triple bonds, also known as alkanes, alkenes, and alkynes in organic chemistry. So they make a lot of double bonds, single bonds, and triple bonds with other carbons. It's very common. Good news is we don't come across too much of that in this class. When we go to organic, you'll see a lot more of it. Any questions on that there? So when we're talking about covalent bonds, which is sharing of electrons, how do we know how those electrons are going to be shared? How can we maybe determine if they're going to be shared equally, if they're going to be shared unequally? Really, the biggest thing that we look at is our friend that we talked about in the last chapter as well, electronegativity, which, a reminder again, is the ability of an atom to bring electrons towards itself. Remember, we talked about the periodic trend, right? And the periodic trend for electronegativity is, as you go up and to the right, it increases. And as you go down and to the left, it decreases. Our most electronegative element is our friend fluorine. Yeah. Fluorine is the as upper right as you could get, except who is to the right of it? To the right of it is the noble gases, right? And the noble gases are chemically inert. They're not really looking to do much, right? So they could really care less about collecting electrons, right? Because they already have enough. So that's why we kind of tap out in terms of electronegativity at fluorine, because past that is the noble gases. They're not looking to change, basically. Everybody else is looking to change to become like them. They actually have like 0 in terms of electronegativity, is what you sort of consider in most cases. The noble gases, they're again not looking to do much by taking more electrons on or anything like that. The reason they wouldn't want to do that, obviously, is because then they would move off of the noble gas configuration, right? They'll no longer be in that stable configuration. So electronegativity is really what helps us distinguish how the electrons in a covalent bond are going to be shared. This is what is sometimes referred to as bond polarity. So bond polarity is when we use electronegativity to sort of help us decide how those electrons, again, are going to be shared between those 2 atoms in that bond. So if we look at something like what we saw previously, which was hydrogen, and hydrogen, obviously, in this case, going to make our bond like we saw here, or we're going to have a hydrogen bond like this. Now, in terms of electronegativity for hydrogen, it clearly is going to be the same electronegativity value, right, for the hydrogen on the left as it is for the hydrogen on the right, because they're both hydrogen, right? So they're both the same element. So what that means is when we have something like hydrogen and we think about how the electrons are going to be shared, they are going to be pretty much shared equally between those 2 guys, because they're going to be attracted to the hydrogen on the left just as much as they're attracted to the hydrogen on the right, right? So you could kind of think of it like tug of war, right? You got like a little rope, right? You got a little flag in the middle, right? And if you got 2 people on the opposite sides pulling exactly the same on that rope, the little flag is just going to sit right where it's at, right? It's not really going to go one way or the other. And the result of that here in sort of bonding aspect is we will create equal sharing of electrons. By the way, this also happens with our fluorine that we saw earlier as well, right? The 2 fluorines would have the exact same electronegativity. And that means that if this little smear or whatever I'm drawing on here is the electron sort of density, they're going to kind of be spread equally between the 2. The result of that is we actually end up with something that has, for lack of a better description, no charge, because we got nice equal distribution of those electrons over the entire bond. And this type of bond is what is referred to as a nonpolar covalent bond. Are just normally called by most people just a flat out nonpolar bond. It's implied that it's covalent. They're sharing electrons. Most people kind of leave the covalent part of it out, but it is a nonpolar covalent bond. Now, it results in perfect equal distribution of those electrons. Really, a kind of neutral sort of bond is made. There's no side to say more positive, there's no side that's more negative. It's kind of just neutral. By the way, this type of sharing where it is perfectly equal, kind of perfectly equal sharing. This is also sometimes referred to in some books as a pure covalent bond. A pure covalent bond is still a nonpolar bond, but it has kind of like perfect equals. That's like as equal as you could get in terms of sharing those electrons. So some books will classify that type of sharing as like perfectly equal as a pure covalent bond. It's still nonpolar, still neutral, still going to have equal distribution. Any questions on that there? Now, what happens if we swap out the hydrogen or the hydrogen for a fluorine or the fluorine for a hydrogen, and we look at something like HF? When we take something like HF and put them together, we now will have differences in electronegativity. So as we know from our general trend in electronegativity, the most electronegative element is fluorine, right? Which would argue that fluorine and hydrogen, when it comes together, the fluorine is going to go, I would like the electrons more than you, right? So what's going to happen is, because fluorine is more electronegative in this bond, what we will actually start to see is the electrons starting to head a little bit more towards the fluorine side and a little less of them kind of hanging out near the hydrogen side in this particular case. Now, the consequence of this happening is when we look at this particular bond here between H and F, if all of the electrons are going to kind of head towards the fluorine, will the fluorine be more positive or more negative? Or will it still be neutral if all the electrons decide to vacation near the fluorine? So if all the negatively charged electrons decide to vacation near the fluorine is actually going to pick up what is referred to as a delta negative, or a partially negative charge. That's a delta symbol, by the way. And that is a partially negative charge. The hydrogen, which sees its electrons kind of heading towards the fluorine, will now pick up a partially positive charge, because those electrons are kind of moving away from it, right? It's kind of electron deficient in a sense. The fluorine is becoming more electron abundant in that case. We can represent this as well with an arrow, and this arrow is what is sometimes referred to as a dipole arrow. And when you draw this dipole arrow, the point of the arrow always points to the more negative side, and the back part of it, which kind of makes like a plus sign, is always to the more positive side of the bond. So we oftentimes will draw these arrows to represent that there's unequal sharing of electrons. And when you have this unequal sharing of electrons, you get what is referred to as a polar covalent bond. Or more specifically, most people leave the covalent out, and it is a polar bond in this case. Yeah. Again, they're the same thing. Why is the fluorine has a partially negative charge and the hydrogen has a partially positive charge? Why do they not have a full positive charge and a full negative charge? That's exactly right. even though they are being shared, which is the key word there, they're being shared unequally. They're not being shared, which I don't even know if it's the right way of saying that. They're not really being shared so unequally that the electrons have jumped ship, right? Like we have in an ionic bond where we have those two guys coming together, electrons from the metal is just going to jump because of the trends. Here, there is still some aspect of sharing happening here in a polar covalent bond, which is why we get partially positive charges and partially negative charges, rather than what we see again in an ionic bond where we get the full transfer of electrons from the metal to the non-metal, which creates a fully positive guy and a fully negative ion that forms in that particular case. Any questions on that there? All right, I'll lay it up there because it's